basically centered around this. And then there's just the simple circular motion problems. You got some satellite traveling in a circle, in which case you have the force and the acceleration is v squared over r or omega squared r. I don't know if I need to do one of those or where you want me to go at this point.
You could do one of those.
Let's figure out what, let's figure out how fast Mars is going. What is
Okay.
the speed of Mars? With respect to the sun. What's the speed of Mars with respect to Mars?
Zero.
Zero.
Oh, yeah.
I learned something.
I'll give you a hint now in case you have it for 252. There's a relativity problem where these travelers go to a distant planet and come back, and I say, how far did the travelers go with respect to themselves?
Is that the end? Is that the
Is it nowhere?
How far did they go with respect to themselves?
Nowhere.
Nowhere. Oh.
With respect to
The other
themselves.
thing- yeah.
Like that. Can we have problems like that? Yeah.
I'd still find a way to overthink
But
it.
There's no partial credit problem with that, though. All right, so we have Mars and Sun. Mars going around. We will assume circular orbit because the orbit is just way complicated. I don't know if you've watched the Kepler videos.
I did not delve into those.
Yeah.
But I did subscribe.
Force diagram.
Right. And then back, right, okay.
So Mars is being attracted to the Sun. Sun's being attracted to Mars.
And that's it.
Yeah, that's it. There's no air resistance.
Right.
That's really-
Oh, yeah. I still haven't
That's-
watched the Dragon videos yet, and I'm kind of afraid to.
Most I heard
Right
from
video?
stairs up in all space, right?
So, I mean, we're still going through the facades method here.
Okay.
Force diagram done. What's the direction of the acceleration?
Towards the center.
Yes.
Because it's centripetal motion.
Okay.
So we have acceleration going in that direction.
Do it again.
Oh, no.
Is that pass the test?
There's only,
The acceleration is not part of the force diagram. This is just here as a separate item.
okay.
Is acceleration, do we denote that with K hat, R hat? Is that how we denote it?
It would be in the negative r hat direction with the sun as the central object. But since my force is in the same direction as the acceleration, we, just like when we do our other F equals ma equations, we don't have to put in the r hat. Coordinate axes, well, it's a one-dimensional problem, and the fact that I have forces in only one direction, accelerations in the same direction, I'm just gonna make towards the center positive.
Okay.
I don't have to decompose anything, so what I'm left with is
Great.
my equations of motion.
I have,
So it would be just FG minus FG.
well, FG plus at the acceleration, right?
It'd be,
Oh, no, sorry.
F of G on Mars plus the acceleration minus that.
No, because it's gonna, the equation is F equals ma. So whatever we put is gonna be equal.
Yeah.
The acceleration's gonna be on the other side.
Well,
of
the force of gravity from Mars is going in the direction, or the positive.
do we replace, are we substituting equations?
Yeah, just, but the basic equation of motion is Fg equals ma sub c
Gotcha.
for centripetal acceleration.
And then we can.
Because when you're doing the when you're doing the equations, you're doing the equations for a particular mass. So we're doing the equation for Mars here, We're not doing it for the sun, we're doing it for Mars,
So it's,
and so I have only one force acting on Mars.
Oh.
I'm not doing it,
Uh,
I'm not doing
Okay.
F equals MA for everything involved here, because then you end up with 0 equals 0.
yeah.
Oh.
So FG
Yeah.
equals MAC.
Alright, so now substitution,
Then-
we have a formula for F sub G,
And you can do AFC as MV squared over R.
so plugged in for A sub C, right there. That's F sub G. Now, I do have two masses here, I just generically wrote M1, M2, but specifically, the two masses involved in this force are Sun and Mars. Let's actually just use S and M.
Okay.
This mass here is mass of Mars.
Yeah, and then we can simplify that. It'll
Yeah.
just go down to
So what
G.
can we do to simplify it?
That M will cancel one of the M's on the other side.
Which M am I getting rid of?
The
I
mother
think
mass
the
of
one
Mars.
of
Yeah, mass of Mars, I can't just get rid of, I can't get rid of mass of Sun.
Right, because that's the mass of Mars anyways, right?
R
Yeah, yeah.
squared.
So mass of
Yeah,
Mars
get
is
rid of one of the R's.
one of the R's. Then we got V squared equals G
GMS.
MS over R. So,
So we take
So
this.
you get square root of that?
Yep.
G,
So 6.67 times 10 to the negative 11 times mass of the Sun
mass of
divided by the distance between Mars and the Sun. Right, or this.
which I'm gonna guess it's pretty far.
It's
I was hoping you would narrow it down a little bit more than that, but yeah, that is true.
I got you. It's gonna be more than 1 mile.
All right, we're getting
It's
there.
gonna be more than one AU.
Oh.
That is true as well.
Less than 2 AU.
Less than 2.
All right,
What is it?
this textbook does not want to put all that information all in one spot.
That's
Ooh,
smart.
Can I access the internet here? Sure, I can.
It is just a big Android tablet, right?
Yeah, that's what.
yeah,
Kindle.
Yeah, I'm pretty.
It should have internet.
Well, let's just save a little bit of time here, and if somebody could look up what the mass of the Sun is.
Uh-oh.
Oh.
Oh god, the Kindle's not.
Something times 10 to the 31st.
1.989 times 10 to the 30.
10 to the 30th.
Kilograms.
But, yeah,
1.989 times 10 to the 30.
yeah.
30, okay.
Yeah, no,
And Mars to Sun distance,
Oh.
Wait, so the negative 30?
the positive 30.
Positive.
Yeah, mass of the Sun is bigger than mass of me.
I was giving it in
In kilometers.
Yeah, it's giving.
I got the distance is 226.31 million kilometers.
226 points.
31. If it's million, it's to the times 10 to the 9, right?
Times 10 to the 9th meters.
Yeah,
It was 10
that's
to
a
the-
million.
It was a million kilometers.
It was 226.31 million kilometers
226 million kilometers, so
to the
so a million is 10 to the 6th, and then
Six.
kilometer is 10 to the 3rd, so 10 to the 9th.
Oh, so
Oh,
we're
that's what
making
I
this
meant.
meters. This is gonna be meters per second?
It better be. If it's not meters per second in the end, then we've done something wrong. Will?
Are we assuming a perfectly circular orbit?
Yes.
Okay.
Oh, yeah.
Okay.
While I'm thinking about it, paranoia check. Yeah, we've captured all that brilliance that's been. And anyone actually,
I ain't got that far.
Okay, give me a second. Actually. 6.67 times 10 to the 11 times 1.9 times 10 to the 30 over 10 to the 9. 5.862 times 10 to the 30 meters per second.
that's 10 to the 30?
Yeah.
I got.
Wait,
It's
oh,
really point.
I did 10 to the I did 10 to the 11th, not 10 to the negative 11.
Alright.
2.42 times 10 to the 13th.
I have blundered.
And we got confirmation, someone else?
I got 24,211.
That's what I got as well.
Is there,
Yeah,
you
so
can do the square
what's
root
the,
of that.
what exponent does it go? Or is that?
Oh, it's the square root too?
Yeah, I got it.
Cause that's 226 times 10 to the 9th, so that's 2.26 times 10 to the 11th. And that's roughly 10 to the 11th, 10 to the negative 22, so 30 minus 22 is 8, square root made it to the 4, so this is making more sense to me.
Hold on.
I got 24,208.
I got you. I got 24,211.87573
Meters per second.
meters per second.
Thank you. That answers the next question. That's not a W, that's an approximate sum.
Oh,
Approximately, yeah, that's about right. Oh, I see why my answer was wrong. I put a 7 instead of a 1.
Ah, that'll do it.
That'll do it. Yeah.
Oh, I
24, I
got
got
11.
86,950 meters per second.
86,000?
950 meters per second.
That's really fast, look. That's really fast.
24,000 meters in a second.
That's
I suspect that you're off by a factor of the square root of 10. If you divide by the square root of 10, do you get this?
Oh.
Divide by the square root of 10.
Same thing
Yeah.
happening with us right now, right?
You're 80 whatever thousand.
We're moving some really fast numbers, but we are not moving.
Yes.
Okay.
Well, no, I get 27,496.
Okay, maybe that's not it.
Okay, well, I add 6.67 times. Oh no. Yeah, I think that's where I messed up.
So that number out there is the speed of Mars going around the sun.
Yes.
Yeah, so.
That's pretty cool.
It was gonna be a really like kiddish question, but so we're going some sort of speed like that too, right, around the sun?
We got.
Yeah, I mean,
But we don't feel it. Like you said, relative to myself, I'm not moving, and I don't feel like I'm moving. But we're moving that fast. But no one like. Why don't we feel it?
it's not like there's wind in our hair from outer space.
That's true.
That would be bad.
This is kind of
Think
how.
how fast are we traveling around the center of the earth right now?
Probably pretty quick.
Probably pretty quick.
But if we
Yeah,
went
we
to
don't
the
feel
center
that
of the
either.
earth, we'd feel the same.
What?
If we went to the center of the earth, we'd feel the same.
The center of the earth, we weigh nothing
Oh.
At the center of the earth.
at the center of the earth.
At
Like
the
if we
center
made
of
a
the-
suit and we could somehow get down there.
Yeah, we would weigh nothing. Because the gravitational pull would be equal in all directions.
Ah.
So the net force, the net gravitational force would be 0.
That's kind of crazy.
That this formula here, if we assume a constant density throughout the Earth, the Earth, and then set up an axis here, where this is the gravitational force and distance. So we have this 1/r² relationship if we're outside the Earth. But if we start going into the Earth, actually, it's a linear relationship. Because at the center of the Earth, I assume that's the center. At the center of the Earth, you are being pulled equally in all directions.
Okay. Okay, that makes sense. Nothing's pulling on you. You're at the center of the earth. The earth can't pull on you if you're at the center of the earth. That makes sense.
Or all the pulls are canceling each other out.
On you, because when
On
you're
you.
getting pulled this way and this way equally, and this way and this way equally. Thus, you're at 0.
By symmetry.
And this way, and this way.
And that way.
Have we ever like?
All 300.
And also that.
Have there ever been like any
How?
what's the word, like experiments or like attempts
Just make a center of the earth.
to get as far down into the earth as we can? And like
I
how-
don't know if we can really get much past the crust, because once we do that, we hit the plasma.
Yeah.
Oh, I remember learning about that.
There's plasma.
Is there like an estimate, like of how
far we can get?
how far it is to the center?
Oh, to the center?
Yeah.
We know
Like-
the radius of the Earth.
Oh.
Radius of the Earth is about 6.38 times 10 to the 6 meters.
Oh, I didn't know that we.
What?
That's it.
And the first person who took an estimate of that got, I think within 20% was whatever, Eratosthenes? There was someone in Egypt who set up an experiment a couple thousand years ago.
It's probably, yeah.
And that's at sea level, I'm guessing.
Yeah.
At sea level?
Yeah.
Well, considering the error bars, I don't think it really made that much difference there.
Okay.
But it's basically, you had to do it at, when the sun was directly overhead here, so there'd be no shadow, and then you'd have another light someplace else where there'd be a small shadow, and then based upon the length of that shadow versus the length of this shadow, you could predict what the curvature of the earth is.
Whoa.
That's crazy.
Whoa.
And you know how far away the sun is, but you can do that in theory simply enough, like triangulation.
Wow. Very, very cool.
That's freaking.
That's really cool.
That's neat.
Wow.
All right, other questions right now? All right, I'm gonna talk about energy and work.
Yeah, what? We might get into work and stuff. We might get some.
All right, so last Thursday, we started talking about, I derived the formula for kinetic energy that I just released. And we just touched on potential energy.
Potential.
The symbol for potential energy.
It's just a U, right?
Yeah, just a U.
Sounds
There'll be subscripts depending on which type. But the formula for kinetic energy, 1/2 mv squared, which, and I spoiled it for you, I should have had all of you answer in unison. But potential energy, if I ask what's the formula for potential energy, what is the correct response?
Which one?
Okay? And so there's one for every conservative force. So, for every conservative force, there exists a potential energy.
What?
That's the
According to
backwards E.
I have
What did
never
you
seen
just
this.
draw?
They just don't do that in math anymore. This is for every, and this is there exists.
What?
For
For
every.
every conservative force, there exists potential energy.
I think my
For
algebra
every
is that
conservative force.
on that.
Bro.
It's a public outrage right here, dude.
If you left the board before all that, and then it got lost in time and they found it 2,000 years later.
I know, they're gonna be
Egyptians
like, what's
or
this,
something.
this advanced humankind, must have been an alien.
What kind of alphabet is this?
Anyway,
Yeah.
and the conservative forces, I think last time I just sort of gave you the list. Gravitational force, ideal elastic force. And those are the two main ones that we will deal with in this class. And then in the next one, the electric force
Electric force.
and magnetic force, those are also conservative forces.
Okay.
Electric force is kind of.
And there's a formal definition that the book offers.
For each
But
one?
at this point, I just find it easier, just got a checklist. You got a checklist of two things. Everything else is non-conservative. So let's just actually go through derivation. This is in one of the videos, so apologies for repeating that, but I have an object here that is moving away from some central planet. So I have mass 1, mass 2. And I want to figure out how much work does it take for this, how much work is being done by the conservative force as it goes from here to here. So from some initial distance to some final distance. So I'm gonna call this initial distance r sub I, and the final distance r sub f. Work, if you will recall, the calculus version is f dot d x r s, whatever letter you happen to be using, is a dot product In other words, it cares about multiplying parallel parts. And if you broke that down, that would be the integral, the dot product is the magnitude of the force times the magnitude of the other vector, which is our differential, times the cosine of the angle between them.
Times cosine of the angle. So if they're straight on like that, can we assume the angle, or do we have to figure out the angle?
Oh, the angle we'll think through. We'll look at the angle.
Okay. Dang, it crashed.
Oh, wait a moment.
So what if there is
That's really cool.
no angle?
It has the Android OS or whatever it uses to draw and Windows.
Yeah, well, no, I think it's so you can hook up a source to it and.
All right, so I have two vectors here.
That makes sense.
So there's gonna be an angle between them. So when you said no angle, did you mean a 0 degree angle or
Yes, sorry,
angle
yeah.
does not
A
exist?
0 degree angle.
0 degree angle, then cosine of 0 degrees.
Oh, okay.
So A dot B is just the magnitude of A times the magnitude of B times the cosine of the angle between them. That's in polar form. So as this mass is going from Ri to Rf, what is the direction of my differential?
What is the RI of your differential?
As I'm moving from here to here,
Yeah,
what is the direction of dx?
to the right.
To the right.
Yeah. So this is going that way. What is the direction of the force acting on it from the planet?
The other way.
Yeah.
Yes. So what is the angle between them?
180 degrees?
And what's the cosine of 180 degrees?
Oh, God.
Is it 1?
Negative one?
Negative one.
Negative.
So this just becomes negative integral of f dot dx, or f dx.
Okay. Oh, okay.
So when you do the dot product, you end up with scalars, and so scalars are, this is probably looking more like Calc 2.